Hello everyone, my name is Abhinav Reddy Avala and today I'll be talking about text summarization in information retrieval. In this presentation, I'll explain what information retrieval is, what text summarization means, how it works, and how it connects to real-world applications. This topic is fascinating because it sits right at the intersection of natural language processing and artificial intelligence, helping us make sense of huge volumes of data. Information retrieval or IR refers to the process of finding relevant information from large collections of unstructured data. A great example is Google search. When you type a query, the system retrieves and ranks the most relevant documents from billions of pages. Other examples include digital libraries, news aggregators, and chatbots that respond to user queries. Text summarization plays a key role in IR because it helps deliver concise, relevant summaries instead of showing full-length documents. Imagine searching for a topic and getting a short summary instead of a 10-page report. That's the value of summarization. Let's talk about text summarization. So, text summarization is the process of automatically generating a shorter version of a document while preserving its key meaning and intent. This technology is essential in today's world where information overload is a major problem. Summarization saves time and helps users grasp important ideas quickly. For example, a system might read a long weather report about the Indian monsoon and summarize it as the monsoon brings seasonal rains to India each year. This ability to condense data while retaining meaning makes summarization a crucial part of modern IR systems. Let's talk about the types of text summarization. There are mainly two types of summarization: extractive and abstractive. Extractive summarization works by identifying and selecting key phrases or sentences directly from the text. It's like highlighting the most important parts of an article. Abstractive summarization, however, goes further. It paraphrases and generates new sentences to express the same meaning, much like how a human summarizes. For instance, extractive systems might copy key lines, while abstractive systems create new ones in natural language. Modern systems such as GPT, T5, and BART are powerful examples of abstractive summarizers. Now let's talk about how text summarization works. The process involves several key steps. First is text pre-processing, cleaning the text, removing stop words, and tokenizing it into words or sentences. Next is feature extraction, which can involve methods like TF-IDF, word embeddings, or sentence embeddings. Then comes sentence scoring or ranking, where each sentence is assigned an importance score. Finally, the system generates the summary either by selecting top ranked sentences or rephrasing content. Tools like NLTK, Spacey, and Gensim are widely used to build such pipelines. On this slide, we can see the complete process of how extractive text summarization works, step by step. Let's walk through it slowly. We start on the left side where we have multiple articles or documents. These could be news articles, research papers, or web pages. The first step is to combine all the text from these sources into a single large block of text. This step ensures that all the information we want to summarize is collected together. Once we have this combined text, the next step is to split it into sentences. Each sentence becomes an individual unit that we can later analyze. You can imagine this like breaking a long paragraph into smaller and more manageable chunks. After that, we move on to the vectorization step, shown in the yellow box labeled vectors. Here, each sentence is converted into a numerical vector representation so that the computer can understand and compare them mathematically. These vectors capture semantic meaning, that similar sentences will have vectors that are close together in this space. This is often done using word embeddings or TF-IDF representations depending on the method we are using. For instance, TF-IDF focuses on important words while embeddings like word to vec or bird capture deeper contextual meaning. Now, once every sentence is represented as a vector, we can start building relationships between them. That's what happens in the similarity matrix, shown here in blue. In this step, we calculate how similar each sentence is to every other sentence using something like a cosine similarity. The result is a matrix that tells us which sentences are most related in terms of meaning. For example, if two sentences talk about the same topic, their similarity score will be high. This matrix becomes the foundation for the next step, that is, constructing a graph. In the graph step, we treat each sentence as a node, and each similarity score becomes an edge connecting those nodes. Essentially, we create a graph where sentences are connected based on how closely they are related. You can imagine this like a network of ideas. Sentences that talk about the same thing cluster together, while less relevant ones have fewer connections. Once the graph is built, the system uses algorithms like text rank or page rank to calculate sentence importance. This is represented in the sentence rankings block. Just like how Google's page rank finds important web pages based on links, TextRank finds important sentences based on how well connected they are in the graph. Sentences that have strong links to many other important sentences receive higher scores. These rankings tell us which sentences best represent the overall content. Finally, based on those rankings, we select the top few sentences to create the summary, shown here at the bottom left. These sentences are chosen in order, maintaining the original meaning and flow. to produce a concise, human readable summary of the text. What's powerful here is that the system does this without needing to understand the text deeply like a human would. It relies purely on mathematical relationships and graph connectivity, which makes it fast, scalable, and surprisingly accurate for extractive summarization tasks. Algorithms and models. For extractive summarization, some of the well-known algorithms include TextRank, LexRank, and Latent Semantic Analysis or LSA. These methods rely on graph and statistical techniques to find key sentences. For abstractive summarization, we use deep learning models such as sequence to sequence networks and transformer based models like BERT, GPT, T5, and BART. Transformers are powerful because they understand context and relationships between words, making summaries sound more natural and coherent. Now let's talk about how to evaluate the text summarization. To measure the quality of a summary, researchers use evaluation metrics like Rogue, Blue, and Meteor. Rogue compares the overlap between the system's summary and a human written reference. Blue and Meteor, on the other hand, were originally used in translation. These assess how similar the generated output is to the expected text. These metrics are critical because they give an objective way to evaluate summarization models and ensure they produce meaningful results. Text summarization has many practical applications. Search engines use it to display short snippets below search results. News platforms like Google News and InShots use summarization to give brief overviews of long articles. In healthcare and law, summarization helps professionals read through complex documents quickly. It's also used in meeting transcription tools like Zoom's AI Companion or Otter.ai, which can automatically summarize meeting discussions. Customer service systems use it to condense chat conversations for faster resolution. Clearly, summarization has become an integral part of modern informatics and information systems. One way to understand summarization better is to try to implement it and understand how it works. Tools like GenSim provide extractive summarizers that identify key sentences, while Hugging Face transformers like BART or T5 can generate abstractive summaries. You can even compare these with ChatGPT's summarization capabilities. Let's talk about the challenges and future scope of IR. Despite its success, text summarization still faces several challenges. Maintaining factual accuracy is one of them. Sometimes AI models produce summaries that sound correct but include wrong facts. Handling long documents or highly domain specific text like legal or medical content is another challenge. In the future, we expect developments like multi-modal summarization, where systems summarize not just text but also images or videos. Real-time summarization and deeper integration with large language models will further enhance accuracy and relevance. To conclude, text summarization bridges the gap between natural language processing and information retrieval. It enables both humans and machines to handle massive volumes of data efficiently. With advancements in deep learning and large language models, summarization is becoming smarter and more human like. As the quote beautifully says, the ability to summarize knowledge is the ability to understand it. These are the available references which we have referred throughout the presentation. Thank you for listening to the presentation.